Hi everyone, I'm Smriti. I'm a postdoc at University of Utah. So before starting my talk, I will just like to brief about myself. So I'm a master's in geoinformatics and PhD in civil engineering from IIT Indore. I have been associated with the field of glaciology since my undergraduate days. So I've been involved in a couple of internships where I've worked on glaciology. Then I've done my master's project and PhD on Himalayan glaciers. And now I'm a postdoc in NASA HIMAT and NISAR projects. So today I will be talking about the functioning of glacierized catchments in the monsoon and alpine climatic regimes of Himalaya. So my presentation is structured into the introduction where I will be talking about the Himalaya Karakoram glaciers, climate, hydrological regimes. Then in motivation, I will be talking about the key understanding, research gaps we have and the objectives. Then study area and climatic conditions. I have divided my talk today into two studies. So in studies, I will be discussing in details about the purpose of study, the major goals, data used, methodology, results, discussion, conclusion, references, and the acknowledgement. Now coming to the HK glaciers. So HK is composed of Karakoram, Western Himalaya, Central Himalaya, and Eastern Himalaya. The total glacierized area over the HK region is around 42,000 square kilometer with more than 39,000 glaciers. Now here the question arises, why these Himalayan glaciers are important. So around 1 billion of population is dependent on the water which is coming from these HK river basins. World's largest hydropower plants are installed in these HK basins which generate a power of around 27,000 megawatt. Around 6 lakhs area is irrigated from the water which is coming from these river basin, and these glaciers are sensitive indicators of climate change. Now coming to the HK climate. So HK is influenced by two synoptic circulation systems, western disturbances and the Indian summer monsoon. So over HK, if we consider the annual precipitation from 1979 to 2019, Eastern Himalaya receives maximum precipitation as compared to other parts. However, Karakoram receives maximum precipitation in the form of snow. Temperatures are higher over the southern slopes of the HK and the Indo-Gangetic plains as compared to the north elevated portions of the HK. Now coming to the HK hydrological regimes. So HK is influenced by three hydrological regimes. First is the alpine catchments, which receives maximum precipitation in the form of snow from the western disturbances. And these catchments are known as the winter accumulating type of catchments. Next is the monsoon catchments, which receives maximum precipitation in the form of rain and snow both from the Indian summer monsoon, but they receive majorly the precipitation as rain. At the same time they receive snowfall, so they are known as the summer accumulating type of catchments. And third is the cold arid catchments, which are devoid of both the western disturbances and Indian summer monsoon. They are mostly depend upon the glacier and snow melt. Now question comes, why are we focused on these kind of studies over the Himalaya? So over the Himalaya, we have geodetic estimates from Brun et al. 2017 and Sheen et al. 2020 from 2000, which clearly indicates that these Himalayan glaciers are losing mass at the heterogeneous rate. Coming on to the glaciological mass balances. So we have around 27 to 28 glaciers which are monitored over the field using the, from where the in situ data is coming. They are also showing heterogeneous mass rate, but here you can see that these glaciers are very limited and mostly they are having a time series of 10 to 15 years at maximum and mostly after 2000. Now here the question arises on the glacier and the climate interaction. So a study called Kumar et al. 2019 suggested that the Himalayan glaciers are losing mass at the heterogeneous rate using a Remo model from 1990 to 2016. They also suggested that the snowfall highly correlates with the mass balances. Some of the key understandings from these studies is that the glacial-hydrological studies over the HK glacierized catchments belonging to different climatic regimes are very rare. Geodetic mass balance estimates are available at regional scale since 2000. Geodetic mass balances are available for limited glaciers and very short time periods. And the snowfall variability explains the mass balance variability. So some of the research gaps is that the long-term mass balance and runoff series are not available for the HK glaciers. The glacier-climate relationship is poorly understood at the glacier scale, and the glacier mass balance runoff relationship is least explored in the Himalaya. So based on these research gap, I will be talking about the glacier mass balance runoff relationship in the reference Himalayan catchments, and also the glacier-wide mass and energy balance using the energy balance approach. So for this, I have taken two glacierized catchments from different climatic regimes. Panel A for the Dokriani Glacier catchment and panel B is the Chota Shigri Glacier catchment. Now, what is the rationale behind the selection of these glaciers? First of all, these two glaciers belong to different climatic regime. Second is that they both are having sufficient in situ data, which is very much required when you are reconstructing any long-term mass balance runoff series. So, coming on to the climatic conditions of the Dokriani Barmak and the Chota Shigri Glacier. So here the gray bars is for the precipitation, blue is for the wind speed, green is for the relative humidity, red is for the air temperature. Orange bars and blue bars are showing respectively the short wave incoming and the long wave incoming radiations. So Dokriani receives maximum precipitation during summer monsoon and Chota Shigri receives maximum precipitation during winters. The relative humidity and the temperature pattern is almost similar over both the glaciers. However, there is a huge variability in the wind speed on Dokriani as compared to the Chota Shigri. The short wave incoming radiation is higher in pre-monsoon as compared to summer monsoon, in spite of the fact that the solar elevation angle is maximum during summer. This is mainly because of the presence of cloud cover in the summer monsoon. That's why in pre-monsoon, the short wave incoming are higher. Now coming to the study one. So what we have done is we have selected the 8 glacierized catchments which are having some in situ mass balance and runoff data from the field. Then we have plotted the annual glacier-wide mass balances and the catchment-wide runoff of all the 8 glacierized catchments. What we observed is that the Dokriani Barmak, Gara, Nenar, and Hamta, these 4 glaciarized catchments, they are showing high runoff when the mass balances are less. However, the Dunagiri, Tipra Bank, and Chota Shigri, they are showing much more runoff when the mass balances are more negative. And the Shongaran Glacier is showing no relationship between the mass balance and the runoff. So the overall conclusions is that the available in situ data from the 8 glacierized catchments do not show any significant relationship except the Chota Shigri. The joint in situ observations of glacier-wide mass balances and the catchment-wide runoffs are not available for the recent decade. So there is a need for long-term mass balances and runoff estimates for the glacierized catchments. So the major goals is to analyze the long-term relationship between the glacier-wide mass balance and the catchment-wide runoff, and to understand the glacier-climate interaction in the reference catchments. So for this, I have used satellite data from Landsat 5, 7, and 8 and Cartosat DEM to get the snowlight altitudes for the validation of the model. And for forcing, I have used ERA 5 reanalysis data, temperature and precipitation from 1950 to 2020. So for the model, Here the input parameters are temperature and precipitation. Model parameters are threshold temperature for precipitation, threshold temperature for melting, temperature lapse rate, precipitation gradient, and degree factor. Now coming to the mass balance model. So the mass balance model is giving us the daily accumulation and the daily melt. Based on that, it's giving us the daily mass balance series, and on that we are reconstructing the annual glacier-wide mass balances. Here the calibrating parameters are the threshold temperature for melting and the precipitation gradient, which are calibrated using the in situ glacier-wide mass balances and the catchment-wide runoff. Coming to the runoff model, it's giving us the daily accumulation, daily melt, and daily rain, which is leading to the daily runoff series. And then we are reconstructing the annual catchment-wide runoffs. So before going into the details of the result, I would like to discuss about some relationships which we have formed. So for the glacier-wide mass balance and glacier-wide runoff relationship, here we are considering the runoff which are coming from only the glacierized area. So R is the runoff from the glacierized area, A is the area of glaciers, P is the precipitation which are falling on the glacier, evaporation from the glaciers, and B is the mass balance. If the mass balance is 0, then the runoff is mass balanced. If it's positive or negative, then it's imbalanced. And if it is less than 0, then we are considering it as a glacier degraded runoff. Now the next relationship is the glacier-wide mass balance and the catchment-wide runoff relationship. So we are in this relationship, we are considering the runoff which is coming from the glacierized area and the non-glacierized area. Here we are considering the area of both the glaciers and the non-glaciers in order to calculate the catchment-wide runoff. Now coming to the results. So here the gray plots are showing the annual mass balances, green and orange is for the winter and the summer mass balance estimates, and blue blocks are showing the discharge. Both the glaciers are showing limited mass wastage if we consider a time period of 1951 to 2020, and a similar runoff. However, if we consider like period from 1951 to 1979, both the glaciers are showing positive mass balance. This is mainly because of the higher winter mass balance. Over 1976 to 2020, there is much higher wastage on Dokriani as compared to Chota Shigri. Chota Shigri is showing a kind of balanced state because of the same summer mass balances and the winter mass balances. And over 2021 to 2020, over the recent decade, both the glaciers are showing much higher wastage and almost a similar runoff. Coming to the monthly catchment-wide runoff. So here we have plotted the monthly runoff over 1950 to 2020. The blue is for the rain, green is for the snow, and red is for the glacier ice melt. So over Dokriani, the melt is starting from the month of March and peaking in the month of July. However, the glacier melt is starting in the month of April and peaking in the month of August. And the rainfall starts from the month of May and peaking in the month of August. So overall, the highest runoff is coming in the month of August because the rainfall runoff is higher over the Dokriani-Bamak catchment. However, on Chota Shigri Glacier, the rainfall runoff is starting from the month of April and peaking in the month of July for snow melt. For glacier melt, it's starting from the month of May and peaking in the month of August. Overall, the higher runoff is in the month of July, indicating the snow melt is highest. So Dokriani is having maximum rainfall and around 21% as the glacier melt with 38% as the melt from the snow. On Chota Shigri, around 67 to 68% is coming from snow, 10% from rain, and 21% from the glacier melt. Now coming to the glacier mass balance runoff relationship. So we have plotted the annual glacier-wide mass balances versus the mean annual catchment-wide runoff and the annual glacier-wide runoff. So with increasing catchment-wide runoff corresponds to more negative mass balance and vice versa. And there are stronger relationships between the annual glacier-wide runoff and the annual glacier-wide mass balance as compared to catchment-wide runoffs. These results looks quite obvious, but the main purpose of highlighting this is that according to the previous study on Dokriani-Barmak glacier catchment, this is a contrast which we are getting from the long-term estimates. So they have said that with increasing catchment-wide runoffs corresponds to less negative mass balances and vice versa. So and that too they have predicted it with using the short-term in situ data. Now coming into the more details about the hydrology and the climate parameters. So over the Dokriani-Barmak Glacier, summer precipitation is the most dominant. And on the Chota Chigri glacierized catchment, the glacier-wide summer mass balances are the most dominant. Now, talking about the glacier buffer system and the glacier degraded runoff. So we know that the glaciers and runoffs acts as a buffer zone for the downstream people as they accumulate during winters, and in summers they start melting. So what we have done is we have plotted the glacier degraded runoff. Here gray plots is for the annual mass balances, green and orange is for the winter and the summer mass balance, red is for the temperature, blue is for the precipitation, and green plots is for the degraded runoff, and the multi-plots is for the total runoff. So here you can see that for the glaciated runoff is 0 for the positive mass balance years. However, Dokriani receives the maximum glacier degraded runoff in year 2015, and for Chota Chigri it's 99 and 2000. So around 3% runoff of the total catchment runoff is coming from the glacier-wide runoff on Dokriani and around 10% from the Chota Chigri. So there is almost threefold higher contribution of glacier degraded runoff in Chota Chigri as compared to Dokriani-Barmak glacier. So this also clearly indicates that the hydrology of the Chota Chigri is dominated by the glacier-wide mass balances, which I have told and discussed in earlier slide also. And the buffer zones are much more needed in the alpine zone as compared to the monsoon zone. Now coming to the hydrological year. So what we have done is we have tried to validate the hydrological years which we are following using the modeled mass balance and the runoff series. So the upper panel is showing the glacier-wide daily mass balance and the lower panel is showing the runoff. Green is for the Dokriani and orange is for the Chota Chigri. So here you can see that the mass balances are positive from the October, means on the Chota Chigri means it's start accumulating. However, on the Dokriani-Barmak glacier, it starts accumulating from the month of November. So here the daily mass balance series confirms the selection of hydrological year. As for Chota Chigri, we are using the hydrological year from October to September, and for Dokriani, we are using from November to October. There is a sharp rise in the runoff from the mid-August in the Dokriani-Barmak catchment. This is probably because of the monsoonal snowfall that accumulates in June and July and starts melting in the month of August when the temperature rises. The major conclusions from this is that since 1950, both the glaciers are showing limited mass wastage. The mean annual runoff is almost similar for both the glaciers over 1950 to 2020. Available in situ short-term mass balance and runoff data from 8 glacierized catchments do not show any significant relationship except for Chota Chigri. The glacier-wide runoff increases with more negative mass balances and vice versa. The hydrology is mainly controlled by summer precipitation on Dokriani and glacier-wide summer mass balances on Chota Shigri. Glacier buffer system is more important in alpine catchment regime compared to the monsoon catchment regime. Now coming to the study 2, which is the glacier-wide mass and energy balance using the energy balance approach. So why this study is important? Because we have limited data sets from the field over limited Himalayan glaciers. Generally, there are long-term reconstructions using the temperature index model because of its simplicity. There are a couple of available SEV studies in the Himalaya, but they generally investigate the energy fluxes at the point scale, and the sublimation contribution to the total ablation is scarce for the Himalayan glaciers. So here, the major goals is to find the relative contribution of the energy fluxes and the sublimation losses. So here you can see that there are radiations which are coming on the surface. So here the radiation is coming from the sun, which is the short wave incoming radiation. A part of it is getting absorbed, and a part of getting it is released in the short wave outgoing. From both the atmosphere and the surface, the long wave is emitting. There is some kind of energy which is coming to the surface from the rain which is falling on the glacier surface, called as rain flux. Then we have sensible and latent heat flux. So sensible heat flux is the thermal energy which is passing from one material to another, like in this case from glacier to atmosphere and from atmosphere to glacier. And the latent heat flux is the amount of energy which is consumed or released because of the phase transition, such as vaporization, evaporation, sublimation, and all. And then we have conductive heat flux, which is mainly happening because of the temperature difference between the two surfaces. So here the total melt is calculated using shortwave net, which is a function of albedo and shortwave incoming, long wave net, which is a function of long wave incoming and long wave outgoing, sensible heat flux, latent heat flux, rain flux, and the conductive flux. Now coming to the data which we have used is the temperature, precipitation, short wave radiation, long wave radiation, wind speed, and relative humidity from 1979 to 2021 at a grid resolution of 0.25 degree. All these data sets have been bias corrected using the in situ data for shortened time periods. Here we have used as an input data temperature, precipitation. In addition to temperature index, it's using the wind speed, relative humidity, short wave incoming, and long wave incoming. Here the model parameters are temperature lapse rate, precipitation gradient, threshold temperature for precipitation, threshold temperature for melting, and albedo for snow, ice, and debris. So for the mass balance model, it's giving us the daily accumulation, daily refreezing, daily melt, and daily sublimation. So here, daily refreezing and daily sublimation is an addition to the energy balance model, which is not available in a simple temperature index model. So these daily accumulation, refreezing, melt, and sublimation is giving us the daily mass balance and the surface energy fluxes. And with we are reconstructing the annual glacier-wide mass balance and the surface energy flux. Here the calibration parameters are threshold temperature for melt, precipitation gradient, and albedos, which are calibrating with using in situ glacier-wide mass balance and altitudinal mass balances. Now coming to the model calibration and validation. So model has been calibrated using the in situ mass balances. Here is a plot between the model mass balance and the field mass balance. So over both the glaciers, they are showing a good correlation. And model has been validated using the in situ altitudinal mass balances. Here the blue color is for the clean ice and orange is for the debris cover. The stars is for the field observed data and line is for the modeled data. So both the clean eyes is showing a good correlation over the Dokriani and the Chota Shigri. However, debris is not showing as good correlation on Dokriani as compared to the Chota Shigri. The second validation has been done using the in situ temperature on Chota Shigri, as this is a plot between the modeled surface temperature which we are modeling in using some equations, and then we have tested it against the observed surface temperature which we are having from the field. So it's also showing a good correlation over here. Now coming to the seasonal annual glacier-wide mass balance estimates. So these are the mass balance estimates value per season. So we have divided it into post-monsoon, winter, pre-monsoon, summer monsoon. Here blue boxes is for the short wave net, green is for the long wave net, red is for the net radiation, orange is for the sensible heat flux, green is for the latent heat flux, and gray is for the total energy. So on an annual scale, here you can see that the short wave net radiation is dominating over all the other radiations. There is some addition of energy in the form of sensible heat flux. There is some release of energy from the latent heat flux, and overall the positive energy shows that both the glaciers are losing mass over 1979 to 2021. Now coming to the altitudinal distribution of the mean annual mass balance and the surface energy fluxes. So these are the altitudinal values of all the fluxes, annual values. So here you can see that the annual mass balances of Dokriani is little less over the debris cover. This is mainly because of the thick debris cover which is preventing it from melting. Coming on to the short wave net radiation. Here you can see that after a certain elevation, the short wave net radiation is becoming constant and it is reducing. So most of these studies are using short wave net radiation at point scale, considering it as a similar for whole glacier. That is not correct in the real scenario. There is a huge sublimation which is happening over the higher parts of the glacier, and overall the energy is decreasing over the higher elevation, which is indicating that the short wave net radiation has a dominant control over the energy fluxes over both the glacierized catchments. Now, in order to dig the more details about the surface energy balance, what we have done is we have extracted the surface energy balance values both in the ablation and the accumulation zone. So here the blue is showing the short wave net, orange is showing the long wave net radiation, white is for the sensible heat flux, green is for the latent heat flux, and Q is for the total energy. So what we observe is that the long wave net radiation, which was negative throughout the glacier as in the previous slide, was slightly positive in July and August on the Dokriani-Barmah Glacier catchment. This is mainly because of the presence of the heavy monsoonal cover on both the ablation and the accumulation zone. And another interesting result is that the latent heat, which was negative throughout the glacier, is positive on both the glacier in the ablation zone, only in the ablation zone, indicating that there is some resublimation which is happening in the ablation zone of both the glaciers. Now coming on to the sublimation part. So over 21 Himalayan glaciers have been monitored using the surface energy balance, and they are mostly at the time scale. So you can see the spatial distribution of these glaciers, which are being monitored using the energy balance studies, and mostly they are at point scale. And there is a loss through the sublimation around 22% on the Dokriani glacier and around 20% on the Chota Shigri glacier to the total ablation, with a strong spatial and a temporal variability ranging from minus 0.18 to minus 0.27 meter watt per year. The major conclusions is that the glacier-wide shortwave radiation is dominated by the long wave net and the turbulent fluxes. The latent heat flux is always negative, suggesting glacier-wide sublimation throughout the year, except for peak summer monsoon, when it is slightly positive over the ablation zone, indicating resublimation on both the glaciers. The losses through sublimation is around 22 on Dokriani and 20 on the Chota Shigri to the total ablation with a strong spatial and temporal variability. And given the important role of sublimation on these two reference Himalayan glaciers, we stress towards the inclusion of a simplified sublimation scheme in the temperature index models. So overall conclusions is that both the glaciers showed limited mass wastage from 1950. The glacier-wide runoff increases with more negative mass balances and vice versa. Hydrology of Dokriani is dominated by summer precipitation, and on Chota Shigri, it's dominated by the glacier-wide summer mass balances. Glacier buffer system is important, much more important in alpine catchment regime as compared to the monsoon catchment regime. The losses through sublimation is around 22 on Dokriani and 20 on the Chota Shigri to the total ablation with a strong spatial and temporal variability. Given the important role of sublimation in the two reference Himalayan glaciers, we stress towards the inclusion of a simplified sublimation scheme in the temperature index model. So these are the few references which I've gone through. And here are some field photographs which I've been part of. The main purpose of showing these field photographs is that we are collecting the GPS measurements, we are also taking the stake measurements, we are doing some snow density measurements, and we are taking the meteorological data at 5,000 meter. So a big thanks to the people who are collecting data on the field, because I've been to glaciers and I think it's very, very tough job to get data from the field. So big thanks to them. A big acknowledgement to Dr. Mohammad Farooq Azam, who has been part of both these studies and has been constantly guiding throughout. A big thanks to IGS seminar series for giving me an opportunity to talk. A big thanks to DST and ISRO for sponsoring my PhD work. And a big thanks to you all for listening me. So these two works is available, freely available and published. And if you have any questions or any queries, you can reach me out. Thank you.
Thank you very much indeed. So with questions, we usually ask people to indicate in the chat that they have a question that they want to ask. So does anyone have a question for Smriti? I was interested to know whether the current runoff from the glaciers is sort of higher than it will be. Is it increased by essentially mass loss, or are we already in a situation where the reducing volume of the glaciers has reduced runoff?
Yeah. Yep, because over the recent decade, if we see the estimates also, the runoff is higher because the temperature has been increased. We are facing the higher runoff. But if we consider it from 1950 towards the current scenario, then it's when both the glaciers are showing a balanced state. But over the recent decades, both the glaciers are showing much more higher runoff, as it's basically because of the temperature increase, and the precipitation is almost similar, but mainly because of around 1 degree temperature increase over both the glaciers.
Okay, thank you. Does anyone have a question for Smriti? Trevor, do you want to unmute yourself and ask your question?
Okay, thanks. That was very interesting. I'm just wondering a bit about the runoff and how does the runoff occur? Is it mainly superglacial streams or is it subglacial and coming out of the glacier snouts?
Yeah, we are means these estimates which we are taking is the runoff which is coming from the glacier snout. So
Okay.
for yeah, just considering the snouts runoff.
Okay, thank you.
Thank you.
And Ian Evans has a question.
Yes, thank you very much. A lot of interesting data you presented there. Can I just ask a fairly simple question? What percentage of the snowfall is in winter on each of the two glaciers? Or what percentage of precipitation if you can't separate?
Yeah, so around the glacier, which is an alpine catchment regime, it's getting maximum precipitation during winters. So around 70 to 75% of precipitation is coming during winters on Chota Shigri. But Dokriani is receiving maximum precipitation during summers, and mostly it is in the form of rain because of the temperatures, and a very small form in the form of snow.
Right, thank you very much.
Are there any other questions for Smriti?
This is Paco. Sorry, I don't have the camera working. I have just a doubt, and I'm not familiar with the concept of resublimation. Could you tell me a little about it?
Yeah, actually, sublimation is an amount of energy which is lost from the glacier, like snow is evaporating. However, resublimation is how much the evaporated snow is getting accumulated again because of the temperature, decrease in the temperature. So that's the resublimation.
Okay, thanks.
Thank you.
Okay, thank you very much to everyone. And thank you very much to Smriti for a very clear and a very interesting presentation. Next week's seminars are 3 early career researcher talks. We have 2 on Antarctic ice shelves and 1 from Greenland. So I think we'll have a very interesting set of talks next week. But huge thank you to Smriti, and thank you very much to everyone for listening.
Thank you so much for inviting me. Thank you.
And as usual, the seminar will be on YouTube shortly, within a day or so. Thank you very much to everyone.
Thank you everyone for listening. Thank you.
Bye.